There's one or two more things that we should talk about in the context of a three-point test cross. One thing that you might encounter is something along these lines, where you do the mapping and you get two values that are 50 map units, or close enough to 50 map units that the numbers are just slightly off. You have to realize that when you're using real data numbers, oftentimes the data is not going to be exactly precise, especially if you're using real-life data from the lab, say. But let's say you have this situation where you have two loci that are mapping less than 50 map units apart, and then you have two intervals that are mapping at 50. Your first hypothesis in this case should be to place one locus on a separate chromosome. And I'll draw these chromosomes with the centromere in slightly different positions to emphasize that they're different chromosomes. So if A and B are 20 map units apart, that places them on the same chromosome, 20 map units apart. And then that places C on a separate chromosome. What this means is, if these are on separate chromosomes now, that this interval will map as 50 map units. Or the recombination frequency, a better way to put it would be to say that the recombination frequency is 50%. The other thing to note, and this is sometimes confusing for students, is that this interval is also 50 map units or 50% recombination frequency. The distance between these two loci doesn't matter when we're now mapping to something that's on a separate chromosome. This interval and this interval are both going to give a recombination frequency of 50%. In fact, anything on this chromosome and anything on this chromosome in any position, as long as they're on the separate chromosomes, will give that recombination frequency of 50%. Another thing that you should be able to do is, starting from a map, work backwards towards the actual output frequencies coming from this trihybrid. All the test crosses that we've done up until this point have given you data and asked you to produce a map. You also should be able to start from a map and work towards producing the data, and that's what we're going to tackle here. So here we have a trihybrid. This has the genotype big A, big B, little c over little a, little b, big C, indicating that these were the two input sets. Now we know that they were the two input sets because they're physically linked together on the same chromosome. So if this came from pure lines, it would have been this as the one parent and then crossed with this as the other parent. And this one would have kicked in this gamete, and this one would have kicked in this gamete to give us the trihybrid. Now, if this is a trihybrid that's ready to go through meiosis, so we'll replicate our chromosomes, then what we can do is we can now start talking about the different output gamete types that this trihybrid can form. Now, if this is the linkage map, 6 map units between A and B and 10 map units between B and C, we'll use these values to help us calculate the frequencies of the different outputs. I'm going to call this first interval region 1 and this second interval region 2. Now, the fact that these are linked, again, does not influence the types of gametes that are formed, but only their frequencies. So what we can do is we can start considering the different types that would come out of here. Now there would be the 8 types as per usual for any trihybrid. We're not going to work through every single example, but we'll do a sampling so that you can see how the calculations are done. Let's start with one of the ones that's one of the inputs. So we could ask the question, what's the probability of getting this gamete coming out of this F1 trihybrid? This is very similar to what we've done with pedigrees. We can actually say what are the requirements in order to get this gamete type. We can say, well, we need big A, a big B, and a little c. So what has to happen during meiosis for this to be the output is that we need no crossovers in region 1. If we had a crossover in region 1, that would shift us over to giving us a big A now matched up with a little b, and then whatever happens over here. So we need no crossovers in region 1, and we need no crossovers in region 2 in order to preserve this big A, big B, little c genotype. So we would say the requirements are no crossovers in region 1 and no crossovers in region 2. Now, what's the probability of no crossovers in region 1? Well, if it's 6 map units apart, the probability of a crossover is 6 map units, which means the probability of no crossovers is 1 minus 6 map units, or 6%, which would give us 0.94 as the probability for no crossovers in this interval. No crossovers in region 2, well, 10 map units for region 2, which means the probability of a crossover is 10%, and the probability of no crossovers is 1 minus 10%, which would give us 0.90. Because we say and, we need this to happen and we need this to happen. Remember, and is our reminder to use the product rule. It would be 0.94 times 0.9. But another thing to remember here is that this sequence of events, no crossover in region 1 and no crossover in region 2, produces 2 gamete genotypes at the same time. If I had asked the question, what are the requirements to make a little a, little b, big C gamete, we would have the same things. We would say, well, we need no crossovers in region 1 and we need no crossovers in region 2. So what we've calculated here is in fact the probability of this gamete or this gamete, one or the other. So another way to put it is, this same meiosis will produce one half that looks of gametes that look like this, and the other half of the gametes will be this particular genotype. So in order to calculate the final probability of one of the gametes, we need to take this value and multiply it by 1/2, because these two are equal in frequency. So the final value for this gamete would be 1/2 times 0.94 times 0.9. And if you work that value out, that would be the final frequency for this particular product of meiosis. Let's now do another example where we actually have a crossover in one of the intervals. Okay, so let's calculate another one. Let's now ask what's the probability of a little a, big B, little c gamete. Now, what you'll see here is with the little a and the big B and the little c, we need a single crossover in region 1 and no crossovers in region 2. So what we need, the requirements, are single crossover in region 1 and no crossover in region 2. And as we noted before, it's going to be 1/2 of that total value. So the probability of a single crossover in region 1 is 6%. And no crossovers in region 2, as we worked out before, is 0.9. So the total value, or the final probability value for this particular output of meiosis is 1/2 times 0.06 times 0.9. So as a final example, let's calculate the frequency of one of the products of meiosis that requires the double crossover event. 2 single crossovers that affect the same pair of chromatids is called a double crossover. So we could ask the question, what's the probability of a big A, little b, little c product of meiosis? So big A, little b, little c, which requires this double crossover event. Now we can say, well, what are the requirements? We need a single crossover in region 1 and we need a single crossover in region 2. So we would say single crossover in 1 and single crossover in region 2. And 1/2 of those will be the product of meiosis that we're specifically interested in. So the probability of a single crossover in region 1 is 6%, or 0.06. Probability of a single crossover in region 2 is 0.1. So the final probability would be 1/2 times 0.06 times 0.1. Now, if you work your way through and do these probabilities for all 8 possible products of meiosis, at the end of the day, if you add them all up, they should add up to 1. And that's actually something that you should work your way through at least once in its entirety, so that you can see that it adds up to 1 to make sure that you're doing your math correctly. So in a nutshell, this is how you start with a map and work towards the output frequencies of all the different products of meiosis. The previous types of questions all gave you data and asked you to arrive at a map, and this particular approach gives you a map, and now you know the method that you follow in order to arrive at the data, specifically the output frequencies for each of the 8 different categories. So here's the last variation that we should think about as we think about how we could generate data from a map. So here we have now 2 loci linked on the same chromosome. We could say that maybe that they're 10 map units apart. And then the other locus is independently assorting on a separate chromosome. If these are the 2 parental lines giving us the 2 inputs, here's the F1 trihybrid at synapsis of meiosis. We can now ask the same sorts of questions. What's the probability of various gamete types coming out of here? Let's do one of the inputs like we did before. We could say, what's the probability of getting a big D, little e, little f product of meiosis out of this trihybrid? Well, the first thing that we would have to notice, like we saw before, is that we need no crossovers between D and E. So if I call this region 1, not that there's a region 2, but if we call that a region 1, we would say that we need no crossovers in region 1. And we would need the segregation pattern that gives us the little f. Now, the segregation of big F or little f is always going to be a 50-50 probability. So, no crossovers in region 1, which we now, as we mentioned before, that would have a value of 0.90. And we segregate the little f, which has a probability of 1/2. And then, as before, we need 1/2 of that total value, because the same series of events that give us big D, little e, and little f at the same time would also give us little d, big E, big F on the other side of the same myocyte. So 1/2 times 0.9 times 1/2 would give us the probability of this particular output. Okay, let's do one that requires a crossover. So what should we pick? Let's say, what's the probability of a little d, little e, big F product of meiosis? Now we would say, well, we need a single crossover in region 1, and we need to segregate the big F. Okay. The single crossover in region 1 will have a frequency of 0.1. It's 1/2 for any given segregation, and then all of this multiplied by 1/2, because the same series of events that give us little d, little e, and the big F at the same time would also, on the other half of the myocyte, give us big D, big E, and little f. So that's why we have to do that 1/2 as we've done before. And again, you should work through all the different 8 possibilities for this type of setup and ensure that you've done your math correctly and that they add up to a total of 1.